Feedback control systems are often represented as block diagrams. In this video, we shall see how to simplify block diagrams. A differential equation, or equivalently a transfer function, can be graphically represented by a block, and each block has input and output signals. The plant we want to control, the controller we design, the sensor we use are all typically differential equations and hence represented by blocks. A control system is usually a connection of many such interconnected differential equation blocks, and thus it is represented by a block diagram. Plant, sensor, controller, etc. are each a block. They are interconnected in the sense that the output of one can be the input to another block. One of our big objectives in block diagram analysis is to find a single block, i.e. a single transfer function or differential equation between the overall inputs and the output y. In the block diagram shown, there are two overall inputs. One is R, which is the desired output, and the other is D, the disturbance. They are the overall inputs because R and D flow out of thin air into the whole block diagram. They are the real inputs, and all the signals in the block diagrams will depend on them. One of the most important skills is to first convert a given piece of information from a given problem into a block diagram, and that needs practice. Here's a simple example to help with that. Suppose you want to control the speed omega of a motor by modulating the voltage V given to it, and the relationship between the speed and voltage is a first order differential equation. Omega dot plus B omega is BV. You can convert that using Laplace transform into the following relation. Omega is B over S plus P times V. We usually like to work in S domain because then the relationship between input and output becomes multiplicative instead of a differential equation, and that's a lot easier to handle. Anyway, so this omega equal to B over S plus P times V could be shown by a block like this. This block has an input V, output omega, and output is block multiplied by input. Let's say we have a sensor which measures the speed such that the differential equation between the measured speed and the actual speed is tau omega m dot plus omega m is equal to omega. And we can rearrange this using Laplace as omega m, the measured speed, is equal to 1 over tau s plus 1 times omega, and we can show this as a block as shown. The input to the block is omega s and the output of the block is omega m, and the transfer function inside the block is 1 over tau s plus 1. Let's say there is a PD controller that looks at the difference z equal to omega d minus omega m. That is, it's looking at the difference between the desired speed omega d and the measured speed omega m. We can show this difference by a summation junction as shown. The negative part of this is coming from the output of the sensor. The reference is flowing out of thin air because that's the real input. And let's say the controller provides the voltage V, which is having some relationship to the signal Z, and that relationship is Kp times Z plus Kd times Z dot. If you look, this would be called as a PD controller because it's proportional and also proportional to the derivative of the signal Z. In the Laplace domain or in the S domain, we can write V is equal to Kp plus Kd s times Z, and we can show this by a block like this. So to the controller block, Zs is the input, and the output of the controller block is V, which is the input to the plant. And hence, this is the block diagram for the given problem. Note carefully that the overall input to this block diagram is the reference signal omega d, and that's the one that flow out of thin air into the system. As mentioned before, one of the objectives of block diagram analysis is to obtain a single relationship between the overall input and the output. The overall input is the desired omega d. It is also known as the reference signal. The output signal is omega, which is the actual speed. The single relationship between the reference input and the output is called the closed loop transfer function. All the specifications of the output, like settling time, overshoot, etc., will depend upon the gain, poles, and zeros of this closed loop transfer function from omega d to omega. We have two ways to get to the closed loop transfer function. The first option is to do the algebra. We shall begin by writing the input-output relationships for each block. Starting from the extreme right, for the plant block we have omega, the output, equal to g times the input v, where g is a transfer function inside the block, which is b over s plus b. Similarly, for the controller, we have the output v equal to k times the input z, where k is a transfer function of the PD controller. The signal z, as seen from the summation junction, is reference omega d minus a sensor output omega m. And omega m is h times omega, where h is a transfer function of the sensor. Now, since we are trying to find the relationship between the reference omega d and the output omega, we shall eliminate all the unknown variables or signals like v and z and omega m. Note, g and k and h are not unknown variables. They are the known transfer functions. So, starting from the right, first we have omega equal to g times v, but v is equal to k times z, and z is omega d minus omega m, and hence we finally have a relationship that only has omega and omega d, and everything else is eliminated. This we can rearrange easily to get that omega equal to gk over 1 plus gkh times omega d. Hence, the transfer function from omega d to omega is gk over 1 plus gkh, and that's a closed loop transfer function. The second option, to put it facetiously, is to just remember that the transfer function from the reference input to the output for this specific arrangement of the blocks is gk over 1 plus gkh. You see, this configuration actually occurs a lot, so it is worth remembering, and that's our shortcut. Anyway, the whole block diagram above could be reduced to a single block from omega d to omega with the transfer function gk over 1 plus gkh inside, and we can plug the value of g and k and h to get the overall transfer function in the S form. Some common configurations of the block diagrams occur a lot, and hence we can remember them, and they can help us reduce, i.e. simplify the block diagrams without having to do a lot of algebra. Here are three such configurations, and we shall often use them as shortcuts. The first one is the series configuration of two or more blocks, as shown here. This series configuration means the output of one block directly feeds the next block as input. If we do some algebra, we shall find that the output of the block Y is G of the block G is given as Y equal to G times U, but U is K times R, hence Y is equal to GK times R. Thus we can reduce the series of two blocks by a single block from R to Y, and the transfer function inside that block is GK. The second very common configuration is the negative feedback loop, as shown here. The output signal Y in this block is fed back after passing through the block H at the summation junction. Since it is subtracted at the junction, we call it the negative feedback. Note that if you follow the direction of the arrows, you get a nice loop, a negative feedback loop. Let's do some algebra. For the block G, the output Y is G times the input Z, but Z from the summation junction is R minus Ym. Now for the block H, the output Ym is H times its input, which is Y. Hence we can plug Ym equal to H times Y, and we get this. Now note that this relationship only involves Y and R. And let's collect all the Y terms on one side and then rearrange to get Y is equal to G over 1 plus GH times R. Hence we can reduce this negative feedback configuration by a single block, G over 1 plus GH. A nice mnemonic to remember the transfer function from R to Y is forward transfer function divided by 1 plus loop transfer function. Note this carefully. If you follow the arrows from R to Y in the forward direction, directly going from R to Y, we only have G in the path of arrows. Hence the forward transfer function is G. If you move around in the loop, you'll see that in the loop you encounter both G and H. Hence the transfer function for the loop is GH. So the transfer function from R to Y using this mnemonic is forward G divided by 1 plus loop GK. This trick is actually very helpful and more general than is shown here. The third configuration, which is not that common, is the parallel configuration. Here the signal R is fed into both the block G and the block H. Then the outputs of the two blocks are summed to produce Y. Note that even though this looks like the feedback loop, it actually is not the feedback loop. This is inferred by the direction of the arrows. The arrows are always moving forward here. There is no turning back of the arrows as in the feedback loop. Let's do some algebra. The output Y is the sum of the outputs of the G and H blocks. The outputs of the blocks are GR and HR. Hence Y is G plus H times R. And we can reduce the parallel configuration by a single block G plus H. This block shows that the output Y is G plus H times R, and this one block produces the same effect as the original configuration with many blocks. Let's practice all this by an example. In the block diagram shown here, the objective is to find the transfer function from R to Y. We shall do this first by algebra. Algebra always works, even though it might take time. The first step is to define all the signals. You see, in a block diagram we have two items. There are signals, which are represented by lines, which are input and output to all the blocks. And we have transfer functions inside the blocks. Transfer functions are known. So anyway, let's label all the signals. As shown, we have X, U, V, W, T, and of course R and Y. So these are all our signals. Next step is to write the relationship between input and output signals for each block. Let's start from the right and move backward along the top line. So we have Y equal to S times X, X is equal to 1 over S times U, and U at the summation junction is V minus W, and we have V equal to 2 over S plus 2 times R. Now if you go along the lower line and moving backward along the signal direction, note we get W is S times T and T equal to 1 over S plus 1 times X. Now we must eliminate all the signal variables except R and Y because we want the relationship between R and Y. So let's start from the right and move backward along the block. We have Y equal to S times X, but X is 1 over S times U. So we can plug that in and simplify to get just U. But U is V minus W. And then we have V equal to 2 over S plus 2 times R and W equal to S times T. But T is equal to 1 over S plus 1 times X. So we have that. Finally, note very carefully that X is equal to Y divided by S because Y was S times X. Anyway, so finally we have a relationship between Y and R involving no other signal variable. Let's rearrange this so that we have Y terms on one side and we get this relationship. And finally we can reduce this as Y equal to 2 times S plus 1 divided by S plus 2 whole square times R. Hence the transfer function from R to Y is 2 times S plus 1 divided by S plus 2 whole square. This means we can represent the whole block above by a single block from R to Y, and the transfer function inside the block is what we found. And there's a faster way to do this problem, which is to find the transfer function from R to Y. First note that the block S and 1 over S plus 1 in the feedback path form a series junction, and the output of one becomes the input of another. So we can replace them by a single block S over S plus 1 as shown here. Now note that we have a negative feedback loop in the middle, so we can replace it using the formula forward path, which is 1 over s, divided by 1 plus loop, which is 1 over s times s over s plus 1. Now finally we have a series combination of 3 blocks, and we can replace all of them by a product of all of these blocks as shown. And if you simplify this, you'll get the same transfer function from R to Y as before, which is 2 times s plus 1 over s plus 2 whole square. Note that these shortcuts are so much cooler and faster, but they're also a lot more error prone when things get complicated. But algebra always works, and we have computers that can do the algebra for us. Now let's look at a slightly different example. In the block diagram shown here, we have 2 overall inputs to the block diagram that flow from thin air to the system. These are R and D. Your objective is to find the transfer function from R to Y and also the transfer function from D to Y. We shall assume that the transfer functions inside the blocks G and K are given to us. We shall do this problem by algebra first, because algebra always works even though it may take time. First step is to define all the signals. As shown here, we have U, X, Y, Z, and of course R, D. And then next write the relationships between the input and output signals for each block. Let's start from the right and then move backward along the line, and we get Y equal to G times X, but X due to a summation junction is D plus U. Note that when there is no sign shown on the summation junction, we're going to assume by default these are plus signs. If there's a negative sign at the summation junction, that would be shown specifically. Anyway, so X is D plus U, U is K times Z, Z is R minus Y, and Y is the same as from before. Now we must eliminate all the signal variables except R, D, and Y, because we want to find the relationship between R, D, and Y. So let's again start from the right and move backward. Y is G times X, but we can plug in X equal to D plus U. U we can plug in as K times Z, Z we can plug in as R minus Y. And finally, let's rearrange all this, and after simplification, we get by collecting all the Y terms on the left hand side. And finally, we can get Y equal to G over 1 plus GK times D plus GK over 1 plus GK times R. We can represent this relationship by the block diagram as shown. So the above block diagram, which has 2 overall inputs, R and D, and 1 output Y, cannot be simplified into one block. It is simplified into 2 blocks, one from each of the inputs to the output Y. Note carefully how this 2-block simplification actually respects the relationship, which is Y equal to G over 1 plus GK times D plus GK over 1 plus GK times R. And finally, the transfer function from D to Y is G over 1 plus GK, and the transfer function from R to Y is GK over 1 plus GK. There's of course a faster way to do this problem, to find the transfer function from D to Y and R to Y. To find the transfer function from D to Y, let's just ignore R. That is, assume R is 0, as shown here. Now if you see carefully, this is a simple feedback loop with D as input and Y as output. The forward or direct path starting from D to Y has a transfer function G. That's the only thing in the direct connection from D to Y. The feedback path from Y back to the summation junction has K in it, and it's still a negative feedback. And the loop transfer function, if you move around this loop, is G and K. Hence the transfer function from D to Y is forward transfer function over 1 plus loop transfer function, which is G over 1 plus GK. To find the transfer function from R to Y, we first ignore D, i.e. we assume D is 0, as shown here. Now this is just a standard looking feedback loop. Hence the transfer function from R to Y is forward transfer function GK divided by 1 plus loop transfer function, which is also GK. Once again, I want to remind, algebra always works even though it may take time, and we have computers to do all this. The shortcuts may get trickier, and you have to be very good at using them. So always check your block diagram reduction work by using algebra.